So, hello everyone. My name is Raquel Lazcano, and I'm one of the work package leaders within ALCHIMIA. I lead work package 3, which is one of the technical work packages, and it is in charge of developing a platform combining federated learning, continual learning, and transfer learning techniques to improve steelmaking processes. In the following slides, indeed, I'll provide an overview about how federated learning, continual learning, and transfer learning can be leveraged to boost industrial efficiency and collaboration. As my colleague Carmen just said, ALCHIMIA's mission is to provide a platform for the European Union metallurgy industry to smooth the transition to efficient production processes, enriching them with AI capabilities. One of the main problems, hence, is indeed how to apply AI in this kind of context, with the objective of reducing energy consumption, emissions, etc., of the steel sector, while at the same time favoring its green transition and advancing in the European Union strategy towards AI. To do this, ALCHIMIA faces or have faced some important challenges, such as data sharing and data accessing, interoperability, trustworthiness, and user acceptance, and also a need for scalable IT infrastructure, and last but not least, transferability and replicability of the experiments. To tackle all these challenges, ALCHIMIA relies mainly on federated learning. Federated learning is a decentralized approach to AI model training where data remains local and only model updates are shared. In a nutshell, it presents the following advantages. First, it offers enhanced data privacy and security. It also provides improved scalability and adaptability. It helps with reducing communications and the bandwidth used in the model training. And last but not least, it fosters also compliance with AI and data protection regulations, such as the Data Act or the AI Act. Briefly speaking, the federated learning approach is useful in two cases. In the first one is when the data hosted in clients is very sensitive, so it cannot leave the client's premises. And the second case is where the amount of data hosted in clients is so large that the cost of transferring it is prohibitive. Both cases apply to ALCHIMIA, so this comes as a natural solution. In the context of ALCHIMIA, EVIDEN has developed its own federated learning framework to solve ALCHIMIA's specific needs. And what we have done is to provide a tool that is highly customizable, flexible, and adaptable, for which we have full control of the code and architecture, and which in the end allows us to develop solutions specifically tailored to the problem at hand. Briefly speaking, our framework is based on these three pillars. First of all, modularity, because it allows us to implement customizable federated learning pipelines. The next one is adaptability, because it enables us to ensure data privacy by using different privacy-preserving techniques, and also to adjust to the specific problem at hand by supporting different aggregation mechanisms. And the last pillar is customizability, because it favors seamless integration across diverse distributed infrastructures and enhances security leveraging the MLOps paradigm. As I just mentioned the MLOps paradigm, I'm going to briefly describe it. MLOps is a set of practices that unifies model development and deployment, and it bridges the gap between data science and operations teams. MLOps paradigm presents many benefits, but the most important ones are those summarized here. So basically, it accelerates model development and deployment cycles. It improves model accuracy, reliability, and compliance, and it reduces operational costs through automation. The combination of federated learning and MLOps presents ALCHIMIA's unique solution. This solution envisions a central server, which in the slide is represented on the right, and several clients that in ALCHIMIA's case are one per plant of each of the use cases that my colleague Carmen mentioned before. By combining MLOps and federated learning, AI models can be trained in a distributed manner, exploiting synergies among the different plants without actually sharing the real data, and guaranteeing that the deployments are secure, robust, and scalable. Leveraging this solution, the following results have been achieved. First, several models to optimize the internal processes of furnaces have been federated for both CELSA and Fonderia editorable use cases. The models federated include traditional models such as neural networks or decision trees, but also other types of non-AI or statistical models such as EAF, which my colleague Petri will describe, will get into the details afterwards. So this highlights the potential advantages of federated learning. Regarding the specific results obtained, they show accuracy improvements in federated models with respect to the centralized with the local ones, which proves the hypothesis upon which ALCHIMIA is built, especially for those plants where datasets are smaller or of poorer quality. Apart from federated models, we have also put in place a continual learning system, which is integrated with federated learning and MLOps capabilities. This system allows to deploy models in a distributed manner and monitor them so as to be reactive to potential drops in the performance. If this happens, an automatic retraining mechanism is launched, as can be seen in the graph. Through this system, the robustness of the models is increased, and therefore so is their life cycle. Last but not least, the participation of two industrial use cases in ALCHIMIA has enabled us the possibility to go further with collaborative experiments through transfer learning. Generically speaking, transfer learning aims at reusing knowledge from one model to improve learning on another model. In the specific case of ALCHIMIA, the idea is to reuse the ladle furnace model trained with data from CELSA use case to model the ladle furnace process of Fonderia Itorbele use case, specifically through its Bergamo plant. The main advantages this offers are, first, that it reduces the need for large datasets. Secondly, that it speeds up training. And last but not least, that it improves model performance of similar tasks. Additionally, for the industrial partners, it lowers data collection and labeling costs, and it also accelerates the deployment of models in production. As a conclusion, ALCHIMIA presented these challenges. I opened the presentation with these 4 challenges. And as we have seen in this presentation, thanks to the combination of federated learning, MLOps, continual learning, and transfer learning, we have been able to overcome them. Undoubtedly, our main conclusion is that the solution developed in ALCHIMIA can be generalizable, so it can be applied to other sectors, industries, and verticals. To put a couple of examples where this solution is being tested currently, I'm going to briefly describe 2 different projects where this solution is being tested. First, we have successfully tested it in a swarm learning scenario where a model predicts the number of crime occurrences in 3 different countries, Belgium, Finland, and Germany, using sensitive data from European law enforcement agencies. Secondly, we have also tested this in a hierarchical learning scenario that deals with data coming from sensors on industrial machinery that measure different physical units, such as temperature, vibration, pressure, etc. In this case, 2 different models are proposed for this scenario, one for the detection of anomalies in the machines and another one for sensor data forecasting. The purpose of the hierarchical deployment here is to obtain aggregated models for every machine, which is the first level in the hierarchy, and then for every plant, which is the second level in the hierarchy. As I just said, these 2 successful stories demonstrate that ALCHIMIA solution is not only specifically tailored for ALCHIMIA use cases, but can also be used outside this sector and industry and can be generalizable. So this is all from my side. Thank you for listening.